Hi, everybody. I think we can get started. So my name is Hamsa Balakrishnan. I'm a professor of aeronautics and astronautics at MIT in Cambridge, Massachusetts. And I'm also affiliated with the Operations Research Center at MIT. So I'm very excited to be giving this talk today. The talk is on advanced air mobility, and I'm going to talk about what we mean by that. And really, the idea here is to talk about both the promise that this transformation that's happening in air transportation holds, but also some of the challenges and some of the work that we have been doing recently in overcoming these challenges in supporting advanced air mobility operations. Before I go ahead, I want to also acknowledge that this is, I get to present the work, but this is really work that has been done in collaboration with several people, students both currently and formerly at MIT, as well as colleagues at MIT and elsewhere. So what do we mean by advanced air mobility? So this is the vision, and this is an artist's rendition from NASA on what we mean by advanced air mobility. This is, some people sometimes refer to this as air taxis or urban air mobility or drones. It's something that's becoming increasingly a reality when it comes to the news and things that we read about. The vision is highly autonomous, so increased levels of autonomy on board as well as in the decision-making processes to support this traffic. So highly autonomous aircraft, typically electric aircraft moving away from fossil fuels, and aircraft that do short takeoff and landing or vertical takeoff and landing. So you don't need the kind of infrastructure, airports and runways that we would have currently in conventional aviation. And so this is the vision of the future that we have. But interestingly enough, especially when it comes to autonomy and the idea of automation, this transformation is not something that has started, in the past 10 years or, even the past couple of decades, even though it feels that way. It really has been supported by almost a century of transformation when it comes to the air across, from the first flight. So the picture on the left is a picture from 1903, the Wright brothers' first flight. And about 10 years later on the right, we see the first demonstration by Lawrence Sperry of an autopilot. So the idea that you automate the process, including flying of the aircraft in this case, is something that comes very naturally to us as humans. So you can actually see that he wanted to prove, this is at an air show in France in 1914, and Lawrence Sperry, who was the pilot who had designed the autopilot, had his mechanic actually walk out so that people knew that the mechanic wasn't touching the controls, and he has his hands off the controls as well, demonstrating that the aircraft is flying itself. Although all it's doing is staying level and flying steady. But this progression continued, and so this is a New York Times headline, which seems like something that we expect to see soon, but in fact is from 1947, and it's the first robot-piloted crossing of the Atlantic Ocean. So it was a flight from Newfoundland to Oxfordshire in England. The takeoff, the flight, and landing were fully automatic. It was a modified DC Skymaster with a mechanical brain. So this is the 1940s. There were several things that were remarkable. Firstly, doing this almost 70 years ago. But the second aspect, there were people on board. There were observers on board, including civilians. And when you thought about the speculation on what you could possibly use this sort of autonomous aircraft for, this drone for, it was suggested that in fact for peaceful purposes, they could be used as cargo carriers in addition to wartime uses of these drones. And so in a way, this really foreshadowed much of what we think is going to be one of the uses of these autonomous aircraft as to carry cargo and freight. And really, Amazon Prime Air was foreshadowed almost 75 years ago. So that transformation now, when we think about it, is really that this is going to be the future of urban mobility and urban air mobility. This is another artist rendition, this time from Airbus, but the idea that you can have these small aircraft flying around, helping people in their commutes, for package delivery and so on. And so that is still a vision, but what I'm going to try to talk about today is some of the barriers and some of the work that needs to be done in order to make this vision a reality. And the aircraft, so the vision is doing what we did in 1947 with that one aircraft, but doing it repeatedly, doing it safely for large numbers of aircraft, for collectives of aircraft, and not just one demonstration with one aircraft. And if you think about the aircraft themselves, they look very different now relative to that aircraft in 1947. These tend to be smaller, they're electric, they come in many different shapes and sizes and forms and designs in terms of how many rotors they have, whether they're fixed wing, and so on. So this is just 3 examples of such aircraft. So what are the challenges that are that need to be tackled at this level? The first one is one of just the sheer scale of operations that we're talking about now. So depending on projections, tend to always be wrong, generally optimistic, but they are really optimistic. So if you think about, one projection on how many flights per hour you might see over a busy metropolitan area, in this case, Paris, there's an estimate that we expect to see about 20,000 flights per hour by the year 2035. There are currently of the order of 100 flights per hour over Paris. And so you can now see that we're expecting traffic that's several orders of magnitude larger than things that we currently experience. And even in terms of these smaller drones, which are called SUAS, or small unmanned aircraft systems, the FAA estimates that we're going to have 2 to 3 million of these small drones in our skies by 2023. Now, this is probably quite optimistic, but still, the idea is that we're expecting really large numbers. And so the scale itself brings its own set of challenges. The second thing is when we think about the investments are happening, and there's been a huge interest, and especially in the private sector, and a lot of investment in the drone industry. So this is the chart on the left just shows from 2010 per year, the total investment that's happening in some form of these advanced air mobility companies. The darker blue lines like these are investments in drone companies themselves, and the slightly lighter blue lines are on the passenger drone companies. So these are still autonomous aircraft, but closer to the urban air mobility, the companies that are carrying passengers. And so since 2010, we have about almost $7 billion invested, most of it in the past 5 years. And then this is data through 2020. And very recently, last month, there was a report that said that in this sector, in terms of building aircraft, the E for electric and VTOL is vertical takeoff and landing. So essentially these drones, there was about $5 billion in investment in 2021 alone. So if you think about it, it is a very rapid growth on the side of building the aircraft. We still have much less work that has been done in building the what it takes to get more than one aircraft to fly safely and in a collective manner. And that's really where I believe a lot of the research also exists, in addition to designing and manufacturing these aircraft themselves. So what are the challenges? The first, as I mentioned, is that that of just scale. So if we expect 20,000 flights per hour over a metro instead of hundreds of flights per hour, and you have 2 to 3 million small aircraft, then really it is going to be a congested airspace. And so we can ask the question algorithmically, how do we build the tools that can achieve efficiency at these unprecedented scale of operations that we expect? The second thing that really shifts relative to traditional aviation is the competitive landscape. So in aviation, we're used to the airlines being the competing entities which all serve either passenger traffic or commercial passenger traffic, or they serve cargo. In terms of the investments that we've seen earlier, and also the kind of uses that people are envisioning for these autonomous aircraft and drones in general, you now no longer just have those airlines. You do have some of them who've also moved into the advanced air mobility space, but you also have new entrants. And by new entrants, these could be large companies, but they're now trying a diverse set of missions in terms of things like Amazon Prime Air, or Walmart just announced aircraft drone delivery, or Joby that does urban air mobility, or Google Alphabet Wing, and so on. And the competition itself brings its own set of interesting challenges for us to tackle. The first is that with competition, information sharing in order to get efficiency is no longer a given. And in fact, privacy becomes important. They're not necessarily these participants, these competitors are no longer just willing to share all their information in terms of who's on board or what kind of value of payload is on board and where they're flying, their intent, and so on. And in fact, this came up as soon as the US actually proposed a drone identification rule in order to be able to tell where, who is where at any time. And the first thing that happened when the rule was announced was that Alphabet Wing immediately protested, saying that it violates their privacy. And so we really do need to ask the question, how do we enable privacy? So improve privacy, but at the same time incentivize the information sharing that we need in order to achieve efficiency through better coordination. The second challenge that is that comes up because of this competitive landscape is that fairness actually becomes something that we do need to be concerned about. And so one of the objectives, if you look at the FAA's vision for advanced air mobility, is to be able to provide equitable access to airspace for any operator, no matter what their priorities might be, for new entrants and so on, and not just the massive companies that are capable of monopolizing the airspace. And so and one of the issues that came up was when in Australia, in the Canberra airspace, as Google Wing started its operations there, there were concerns about a monopoly in that area. And so we do need to, when we're building these algorithms to manage this traffic, we need to ask the question, how do we equitably serve a heterogeneous set of airspace users with differing missions and differing priorities? And that really is something that needs to be tackled from the beginning as we build algorithms for this system. So that really, as I say, we build this algorithm. The third piece that comes up is the question of who is the we here? So who manages this traffic? In conventional aviation, it used to be the air traffic controllers or the FAA through the air traffic controller. So the picture on the left historically is a gentleman named Archie League, considered the first air traffic controller. This is a photograph of him in the 1920s in St. Louis Lambert Airport. And as traffic increased, you had a little bit more automation, you had more people, and you have displays and decision support built in. But this is still the role of the FAA, or varying by country, there is an air navigation service provider who provides these services, these traffic management services, in a somewhat, regulated by the government but supervisory manner. The one thing that's expected that's to change for advanced air mobility, both drones and urban air mobility, is that in the concept of operations, it has been stated that the FAA will not play an active operational role in managing UAM traffic under nominal conditions. So air traffic management services will not be actively provided by the FAA or a central air navigation service provider, which now means that really there is a need and there is a gap, a technical gap when we think about it in terms of those algorithms for traffic management. They really do need to be developed by research and the research community, both academia and industry, in order to achieve those goals that I mentioned earlier, namely efficiency and fairness, while still incentivizing information sharing, but enabling some levels of privacy as users might need. And really that is at the heart of what, I'm going to talk about a couple of aspects of this today on how we do this algorithmically. Early days yet, but really there is a big need for this in order to be able to actually make that vision that we saw right in the beginning a reality with many participants. So going to that overall goal, this is sort of the first part that I would like to talk about, is some work that we've done in the past few years on trying to move towards scalable, efficient, and fair traffic management algorithms for advanced air mobility, while enabling some privacy through limited information sharing. And here, one of the things to achieve scale is really to become increasingly decentralized. And so we've been exploring things that are similar to the way road traffic operates, namely protocol-based approaches, or these are rules of the road. The ground transportation is a good example when we try to think about this intuitively, because I don't let everybody know, every car on the road know what my destination is when I leave, and yet we manage safety and we manage to have these rules where if you come to an intersection, we have things like, who has right of way if two cars get there at the same time. Otherwise, how do we prioritize traffic, and so on. So really, that's the spirit which we would like to mimic for the air transportation. So we can consider a sort of very simple case where, let's suppose that our airspace, like this picture is super simplified airspace picture. You have to imagine that it's the air. That's broken up into cells. Let's assume that each cell or each sector of the airspace can hold at most one aircraft, so it has capacity 1. And each of these arrows is an aircraft. The tail of the arrow is the current location of the aircraft, and the head of it denotes where that aircraft would like to be in the next time step. So for example, there is an aircraft that is here that in the next time step would like to be in this cell, and so on. And much like intersections and trying to localize, have very local information sharing, we're going to assume that each aircraft, all it will do is to share its intent with the sector it would like to enter in the next time step. In other words, it's in this sector, this aircraft, it will let the neighboring sector out here know that in the next time step, I would like to enter your sector. And so you can have this set up with many more aircraft, and each aircraft sort of lets its neighbor, the sector it would like to enter next, know that it's going to be able to enter. And there's some limited information sharing that sectors can do with their neighbors, and will, in terms of who they're going to hand off, right? So for example, if the sector decides that they're going to move this aircraft to the next sector, they'll say, I'm handing that aircraft off to you. And also any sort of length of queue that's built up in order to give a sense of, well, if this aircraft moves, how many other people can move? So very local, very simple signaling of congestion, so to speak. And what we would like to do in this setup is be able to come up with a protocol which tells us which vehicles proceed and which vehicles stay and which sector they go into, right? Who gets to move and go where in the next time step. So if we look at this picture again, there are sort of three cases that we should care about. The first one is this one, where there is an aircraft in the top left sector that wants to move one sector to the right, and that one's easy because there's nobody here in the sector it wants to enter. There's capacity, since every sector has capacity of up to 1, and so this is easy. You would let that aircraft go. The second case is the one that's shown in green here, namely it is a cycle. So for these blue aircraft, this blue aircraft would like to enter this sector here, but this sector that I'm showing right now is in fact part of what we call a cycle, namely there's a set of aircraft all shown in green, and really the only thing that can happen is each of them moves to the next part. So unless all of them move, none of them can move in a cycle. And really that sort of shows that if you don't resolve it, you're going to have gridlock and nobody's going anywhere. So the cycles become important as well. And so sort of the third case that we have to resolve is something like what we have down here, where there are actually downstream effects. So a decision that we make here really impacts things that are happening behind it. And in these cases, we do need to decide who do we prioritize in the sector based on all the downstream effects that could happen from that move. And so those are the three cases that will become important when we think about designing a protocol. So the solution that we have, this congestion management protocol, really leverages those three things that I talked about before, starting with, well, the cycles are gridlock, and the first thing that you need to do is to identify and prioritize the cycle. So, and you can do this in a very computationally efficient manner. Find all the cycles and make sure that everybody gets to move within a cycle, because if everybody in this green cycle doesn't move, then nobody moves. And of course, if everybody moves one here, then all the sectors in that cycle are occupied, and so these two blue aircraft don't get to go anywhere. They have to hold because they want to enter a region which has a cycle in that time step. Once that's done, we then identify the sector with the highest back pressure. Back pressure is, might be familiar to some of you. It is this notion from queuing theory that sort of is an indicator. It's an estimate of the longest queue behind an aircraft. And so, for example, if you look at this sector here, approaching it from the right, you have a back pressure of 8, because there are 8 aircraft that would move if this last aircraft is allowed to enter the sector highlighted in yellow. On the other hand, in this direction, there are 5 aircraft that would move if you got to move up there. And so that's how the notion of back pressure is used. And once we identify the sector with the highest back pressure, we ask the question, is there a way we can ease that? So given the aircraft that's currently in that sector and where it wants to go, is there capacity available? Can it move? If the answer is yes, you allow all of those flights along that chain to proceed. And if the answer is no, because there are 2 flights that would like to go, then you use a prioritization scheme to decide which one to proceed. And so you have to decide based on some prioritization. I'm going to come in to talk a little bit more about the way we can prioritize it. That's where the fairness aspects might come in. Which operators queue? So is it going to be from aircraft operator who's like an airline, or any other aircraft operator? Who are you going to prioritize, and which aircraft, and use that to decide which aircraft get to go. So what are some of the candidate schemes that we could use? The first one is just purely prioritizing the longest queue, right? Which is pick the one which has the highest back pressure and let it go. We could also think about taking the flights or the operators with the highest accrued delay being if you've already gotten delayed somewhere else because you were in a congested airspace, then we're going to prioritize you here. You could also, there are cases in traditional aviation where you would look at have schedule times been reversed, right? Is some order of arrival being reversed, and then try to prioritizing that. And then a notion of prioritization that we borrow from, this actually comes from cloud computing and resource management, is what's called dominant resource traction. And the idea here is to look and differentiate between whether the that operator has very concentrated traffic, which already has a lot of delay associated with it. So they're imposing a high externality on the system, or is it something where someone is flying in various places and is actually, has very diffuse airspace usage, and to some extent, you don't want to penalize or you don't want to just give somebody more just because they already have a lot, right? So you want to try to differentiate between what their airspace usage might be, and that's the idea of dominant resource traction, or DRF. So going deeper into this, we can use these protocols, these 4 ideas of doing this, and then try to evaluate it on a range of traffic scenarios. I'm just going to show one example, namely the a numerical experiment for 2 hub and spoke cargo operators in Toulouse, France. So this is work that's in collaboration with folks at Airbus, Tony Evans and Max Egorov. The 2 operators, so on the north and west vertiports, and from there, the operator 1 operates, whereas the south and east hubs are dominated by operator 2. And we can ask for these different kinds of prioritization earlier, what happens in terms of efficiency, and also the delays gotten observed or experienced by each of these operators. So this is a little bit of a busy chart. I'm going to sort of go through it a little bit slowly. Let's focus first on the green line, which is the total delay. So it's the delay across all the flights, so both operators, and it's the axis on the left, the total delay. And we see that for different prioritization schemes, we have different levels of delay, and the back pressure prioritizing back pressure has the lowest total delay, and so it is the most efficient. And this is something that, for the case where the sector capacity is, so the airspace is gridded into cells of capacity 1, we can show that in fact back pressure is going to give us the optimal one-step solution. So if you actually took the global view, even though this is only local information, if you did the full optimization on who should move and prioritized it to minimize delays and to maximize efficiency, you would get the same solution as this back pressure solution, even though this is a decentralized protocol. But for the other protocols, you see that random, just at every instant, letting, when you have these, you have to pick one aircraft over the other, you could pick it randomly, that ends up being the most inefficient. And, there's a slight hit in terms of efficiency that you take with both reversals as well as the dominant resource fraction prioritization. Moving to the bars here, what this shows is the light shaded ones, so the red bars are for operator 1 and the blue bars are for operator 2. The lightly shaded ones correspond to the expected delay. So this is the delay that you would get if nobody else was there, right? So it's essentially your the cost that you're imposing in the system, even if you're the only one there. Whereas the dark, the solid shaded ones are the excess delay that is imposed because you're trying to break these conflicts with the congestion with the other operator. And you see in each case that there is a difference for operator 1 and operator 2. The general lesson that we can take away from this is that back pressure emphasizes efficiency, namely the total delay, and it in this case, because they have roughly the same amount of traffic, it also somewhat keeps an even level of split in the excess delays. So solid bars across the two operators. Whereas what dominant resource fraction prioritization does is it explicitly tries to take into account what that expected delay would have been. How much would you have had if you had nobody else there? And so what it does is accounts for that, and it's a different notion of fairness. It tries to make the excess delay proportional to the expected delay. So in some sense, if as operator one, you actually had more excess delay to begin with, you are going to get a little more if you had more expected delay to begin with, you're going to get a little more excess delay just in proportion to that. And so it takes some hit in terms of the efficiency, total delay, but then it allows us to get more fairness in some sense by making sure that the excess delay is proportional to the expected delay. So this work, really what we've been focusing on is trying to come up with ways in which we can evaluate fairness, evaluate efficiency, and come up with protocols that can help us balance these efficiency, fairness trade-offs between operators in this context. So that's sort of the first piece when we're looking at operator efficiency. But the next question that we can ask is really going from that operator fairness, where you're talking about the airlines for these advanced air mobility operations, to customer fairness. And here, really, we mean the customer as in the person who wants the task done and not necessarily the fleet operator. And this becomes important even in the context of something that we're more familiar with, where the shared mobility platforms. So a good example of this is some of these, DoorDash or Grubhub or your favorite Uber Eats shared mobility platform, where typically you have a fleet of vehicles. You have customers who, in this case, might be restaurants who submit tasks, and the vehicles need the platform needs to decide which vehicles do what, and how to best serve those customers. So in this case, for example, let's suppose we have two restaurants. We have a single fleet of vehicles and two restaurants, one of which is a pizza place and the other is a ramen place that are located right about here. The pizza place is customer one, and their end users, the places that the food needs to be delivered to, are given by these orange stars, whereas the ramen place, the tasks are given by the blue stars. The first question we can ask is, what happens if we just pick the most efficient routing, right, with these two vehicles? And the way you would do this is really solve a vehicle routing problem subject to any constraints that you have on the vehicles themselves. And the most efficient solution here looks something like this, where you would you have two vehicles, one of them goes off in one direction, the other goes up in the other direction. The issue with this, while it's most efficient in that it minimizes the travel time or the total delay, is that it really schedules customer two. So all the ramen gets delivered towards the end, and so it's going to be cooled off. It's going to be less warm and less fresh compared to the pizza deliveries. And so the efficient solution is really not being fair to customer two in this case. We can ask, okay, what if I'm super fair and do something like round robin? So keep going. One of customer one, then of customer two, then of customer one, customer two, and so on. And yes, that's going to be fair, but it's going to be extremely inefficient. We can then ask, what happens if I just try to get fairness by dedicating vehicles, right? So I'm going to say one of these vehicles is only going to serve the pizza restaurant, and one of them is only going to help with the ramen restaurant. And yes, that it helps with the fairness aspect, but it actually it's very inefficient, and it loses all the benefit that you get from a shared mobility platform. Namely, if I have a cluster of tasks here, some of which belong to customer one and customer two, it really doesn't make sense for me to have two vehicles go there and do it. A lot of the economies of scale and the benefits in these shared mobility platforms is going to come from multiplexing tasks, namely doing tasks for different customers in the same route, right? In the same vehicle at the same time. And so that is lost here. So if we think about, okay, how do we address this issue, even though, you could imagine they're going to start drone deliveries of food. So, in any of these mobility contexts, how would you tackle this? There are sort of, the main question ends up being, how do we balance efficiency, which is high total throughput across all the customers, with fairness, namely making some sort of equitable progress for both customers in this case, or as many customers as you might have. Incorporating, so one approach might be to say, okay, I'm just going to bring these sort of fairness objectives into the VRP, the vehicle routing problem directly, but that really makes it computationally intractable. So the approach that we've taken, so we're the platform, the solution that we have, we call Mobius, so mobility and us. For fairness, what Mobius does is it tries to look at sort of this problem across two time scales. It divides the total planning time that we have into a number of rounds, and it tries to say that over multiple rounds, we're going to balance both efficiency and fairness so that we get, we don't sacrifice too much efficiency in the name of fairness, but we don't sacrifice too much fairness in the name of efficiency. So I'm going to try to explain that with a sort of simple example, the same example, and then talk a little bit more through some of the intuition on why the algorithm works. So let's think about scheduling over rounds. The same example that we had earlier with customer 1 and customer 2, and with two aircraft, two cars. So with two vehicles, what you would do is in the first round, right? Maybe you had a planning horizon of half hour or something, and you took the first round or first 5 minutes. And I'm looking at. We just plan and we prioritize efficiency. And the most efficient solution then is going to be to go to all the closest points. And so we're going to end up serving all the tasks that belong to customer 1 in that time period. So we prioritize customer 1 now. So in the second round, what we're going to do is we're going to say, okay, let's compensate for fairness now. And so what we would do is go and complete some tasks for customer 2 in order to balance out that gain in efficiency. In the next round, we go back and we prioritize efficiency again. But when we do that, we actually find that fairness is also preserved here. In the next round, so we can go on round 4 and try to prioritize efficiency again. Once again, we get the same number of tasks for both customers roughly, so fairness is preserved. And then in the last round, we just complete the remaining tasks. And so in this way, what we've done is in each round, we're only looking at efficiency. But what we can do is once we have this time scale over which we also start looking for fairness, we can start balancing both efficiency and fairness. The other advantage of breaking this up into smaller rounds is if dynamic tasks come in, so sometimes you're just going to find a new request that's come in a little bit later, we can easily accommodate that into planning in the upcoming round. And so in this way, you can balance both efficiency and fairness. So this approach, this platform looks roughly like this. It's an online platform that, as I mentioned earlier, it trades off short-term fairness, but gets both long-term throughput and fairness. And I'll show some examples that it actually performs really well. As I mentioned earlier, there are many notions of fairness that we can talk about. We initially consider maximum fairness. So maximizing the minimum throughput that any customer gets, but the proofs that we have can extend to any alpha fare. So alpha fare utility functions are a class of utility functions that I use quite often in network optimization, so might be familiar to some of you. But it includes things like getting proportional fairness or anything in between. And really the nice thing about having this is you can plug in a VRP, commercial off-the-shelf VRP solver here. And you can use various variants of the VRP. So you can add pick up and drop off locations, time windows, various vehicle capacities. In the case of drones, really, we have a lot of need for charging, and so return to home, the home base for charging, and so on. All of this can be incorporated into the VRP solver. And what Mobius is going to do, and we'll talk a little, is essentially translate the problem of optimizing this alpha fare utility function over rounds into a weighted vehicle routing problem and solve it. So the problem setup, just a little bit more formally for the next few minutes, I'd like to talk about. So let's suppose that we have uppercase K customers. Each customer puts in a request for each round tau of capital uppercase T. So T subscript K of tau TAS is the request from customer K. X subscript K is going to be the throughput that we allocate to the customer in that round, and we're going to keep track of this X bar K of T, which is really the long-term throughput, which says here is the average throughput that you have received across, so far, right? After some some lowercase t rounds. And what Mobius does, which I described in words earlier, is it's going to try to balance in each round the average platform throughput, which is the sum of these X bar subscript Ks over all the customers. And it's going to balance that average platform throughput with customer fairness. And fairness here means that if you have two customers with backlog tasks, which have pending tasks, then you want to make sure that you're more or less their long-term average throughput is the same for both those customers. And we do this by and the fairness is going to be to maximize this utility function U, which as I said earlier, we're going to start by max-min utility function. So max-min throughput, which maximizes the minimum throughput across all the customers, but this approach can be generalized to other utility functions as well. The rough intuition of what this does over rounds, just to explain what solving it as a weighted VRP does, is if you have a set of vehicles and a set of customers, you could look at this Pareto frontier, which is how much do you get with customer one, how much does customer one get on the horizontal axis versus how much does customer two get on the horizontal axis. And each of these points is a possible solution that you could have, right? It's a schedule for the vehicles that you have. This extreme here would be sort of dedicating all the vehicles to customer one. This extreme here would be what happens if you give all the vehicles to customer two. And then there are different points in between. And really this red dotted line is the Pareto frontier of what you can achieve. What we're going to look at over rounds is really try to get to this point, right? Which is the intersection between the green line and the dotted line, which is our target allocation, since that is the equal allocation line. And the reason the way we would get here is to sort of between rounds, choose either this point or this point at the right frequency in order to actually, on average, get to closer to this point, which is a higher throughput solution than the B itself. So in other words, just in words, scheduling on this green boundary, the convex boundary, instead of the Pareto frontier, what it does is it gets long-term efficiency and fairness over just getting short-term fairness. And so that's how, that's intuitively how this thing works. Okay, so I wanted to sort of end with a couple of examples of doing this. The first one is going back to aerial sensing drone example, where we now have, let's say, a fleet of 5 drones here, each with the battery life of 15 minutes, after which you have to get back to base and go out and charge and go out again. So these are things that we actually fly. These are, we have, this is map, you can't really tell, of Cambridge, Massachusetts, we have 5 customers, which are 5 applications, each of which wants to do a set of tasks. And these tasks are spread across the city. So what are the tasks that we're interested in? So there's one that's just sensing traffic, where we essentially have these video algorithms that are trying to estimate the speed of traffic on the ground using drones. There's another, which is a parking task, where you want to monitor the parking lot and tell how many spots are free, how many cars are there, and so on. A lot of these drones actually rely on cellular connectivity, especially if you want to fly beyond line of flight. And so we're constantly also running iPerf to monitor what the cellular throughput is in the air. And so that's another task that we want to be doing. There are air quality inspection sensors that we have on the drones there, where we also want to be monitoring air quality in certain locations. And then we want to be doing roof inspections, so infrastructure inspections as well. And these are not all in the same locations. These tasks are spread across the city. You can see here the sort of the teal points are where we want to monitor traffic that's near a bridge and some of the more congested parts of Cambridge, if you're familiar with it. The red points show the parking lots that we're monitoring. The air quality points are out here in magenta, and then the roof inspection is on this side. And the throughput, the TCP throughput, cellular throughput, we want to be doing on a grid across the entire area. And the question here is, how do we efficiently share, right? Efficiently multiplex tasks from these different operations on each flight in order to serve all these applications in an equitable manner. But also the importance of multiplexing is really you get efficiency by doing several things at the same time. And that the other reason why it's going to be important to multiplex is the tasks are not all alike, even temporally. So the traffic, for example, you want to monitor continuously because traffic keeps changing. Parking, you want to maybe go back every 10 minutes. iPerf, which is the TCP throughput, you just want to keep doing cyclically across the entire grid. Air quality, there are just tasks that come up at one time and then you're done. So once you monitor it, and the same thing for roof inspection. These are dynamic things that come up and then you're done with it. And so if we run this, and this is something that we actually have, these are results of real experiments, you can sort of compare 3 algorithms, right? So one is Mobius, which is our solution where we are maximizing the minimum throughput of any one of these apps. The second is an algorithm which is just maximizing throughput, not caring fairness. And the third case is one where I have 5 applications and 5 drones. So I just dedicate one aircraft to each of those applications. And what we notice is that if you dedicate drones, you're going to be fair, yes, but you're actually going to be pretty inefficient. You're going to have much lower throughput, especially because in this case, the roof app, the tasks show up late. That vehicle is going to be sitting and doing nothing until the app shows up, and so you have much lower throughput. The interesting thing for us is really that with Mobius, you get almost the same throughput as you do with the maximum throughput solution. You only take a small hit in throughput, but it's a much more balanced thing where, for example, the air quality app, we don't starve. We're actually monitoring that and dedicating resources to that, whereas the max throughput solution sort of does the iPerf a lot because it is very predictable and it doesn't necessarily want to go out and send flights out here to do the air quality solution, but we have managed to do that as well. And so the nice thing here is even with this sort of dynamic tasks coming in, you can get almost maximum throughput or not sacrifice too much throughput, but actually get good quality of service and equitable service across these different tasks. The last example of this platform is something that's not in the context of aerial sensing, but is in the context of rideshare. And really, this is, if you think about urban air mobility, this is going to be a similar issue that we'd want to do there as well. But this is looking at New York City rideshare and on the ground currently. So if you think about one of the problems that has been noticed in these rideshare applications, there's this idea of destination discrimination, in the sense that there are some locations where you occasionally get demand, or they're not the busiest locations. And so nobody wants to go there, right? It's really hard to find a driver to go to certain destinations. So we want to not have that. We want to mitigate that in some way. So this based on data from these are Lyft rides over a 12-hour period. What we can look at is divide this is New York City into 40 zones, and each zone is a customer for us, right? And it's going to be all locations, all addresses within the zone, and there are going to be ride requests that come from each of these zones. The plot on the right is just showing the top 1,000 of these, and you can see that there's a lot more requests out here in Midtown Manhattan relative to further out to the north and so on. And so the question that we try to ask using Mobius is, can we schedule, we have 200 vehicles here to satisfy these ride requests, which are the tasks, at an equitable rate. So make sure that we are serving all the demand that is showing up from these 40 different zones. The planning horizon that we're going to look at, even though there's multiple hours, is each time we're going to plan for 45 minutes, and we're going to replan to allow for, because there's very dynamic demand, we're going to replan every 10 minutes when new demand comes in. We're going to assume that the demand is volatile, because it is in practice. So if we don't confirm a ride within 10 minutes, the ride's going to be canceled. So it's going to go away, and we'll lose throughput. So we want to keep that up. And as I said, we use a commercial off-the-shelf VRP solver, Google. We use OR tools in this case with a 3-minute limit on each call to the solver. So what are the kind of solutions that we can get here? So we find that we can, once again here, we can get fairness with little loss in efficiency. So these are plots. It's a pictorial depiction of where we're serving a lot of rides. What we want to see, let's start with the max throughput solution. So this is if we solve the problem to maximize the number of rides that we satisfy, right? The throughput. We find that it's very imbalanced, in that this dark, these really bright color here shows that a really large number of rides. There are regions where there are almost no rides that are served because demand is a little bit lower, but we're basically starving those regions from traffic. What we want, if we're very fair and equitable, is more homogeneous colors, sort of like this dedicated vehicle case. But in that case, we don't want to lose throughput. And what we find is that Mobius, our solution, the maximum throughput solution, can actually get to close to within 10% of the total throughput, but get a much more even distribution, a much more equitable solution, or a homogeneous distribution. The plot on at the bottom is the same figure, just showing it differently without the geography. Each of these blocks is one zone, and the width of that zone, that block, shows how many rides we satisfied in that, the throughput of each of those customers, each of those zones. And we find that the difference between the total red, which is the Mobius solution, and the total blue, which is the max throughput solution, is only about 10%. So you get to close to that throughput. Now, fairness would mean that those blocks have almost the same width, and you can see that the max throughput solution has a lot of variation between, very thin bars and very thick ones, whereas you get much more even distribution across customers because the demand is there, and with almost the same throughput, so within 10%. Dedicating it gets very even bars because you're pretty much fair, but you also have a big drop in throughput in doing it. So this is sort of the piece of the second case that I wanted to talk about. I sort of wanted to end with where a lot of this is going forward. So one is about a week, 10 days ago, Walmart announced that they're going to begin large-scale drone operations in 34 sites by the end of this year for drone delivery, partnering with Drone Up, a startup that Walmart's partnered with. they're going to potentially reach 4 million US households, and multiplexing is going to be a big part of this, because they're going to charge only of the order of, I believe it's $3.99 for drone delivery. So for the cost of the delivery will have to get offset with revenue from other services, right? Like insurance inspections and construction oversight and so on. So, much like this is another motivation for the multiplexing that I talked about when we talked about Mobius. And then another application that we're really interested in is, NASA has a collaboration with the Japanese aerospace agency, JAXA, to use drones for disaster response. And here, there's really search and rescue, and there's a question of multiplexing. How do you plan this as well? Because there's some level, you need to first do the search to identify where you need to rescue people from, and then run the rescue operations with helicopters as well. And so we're trying to see where the ideas that I talked about would could get translated to better coordination and better balancing of search and rescue operations. So sort of to end again with the vision, as I said, this really is a really exciting time in air transportation and advanced air mobility. We have a lot of challenges it is a very nice, very compelling vision, but we have challenges in terms of both the scale of operations and the competitive landscape. And ultimately, what we would like to do is build solutions that can allow efficient, equitable, and sustainable access to airspace for all the people all the operators who want to use them, right? So there's a range of vehicles and services. So with that, I am happy, thank you again for the opportunity, and I'm happy to answer any questions.
Thanks, Hamsa. This was a really great topic, and everybody's super excited about this. I kind of wanted to ask some sort of general questions about this. I noticed that a lot of car manufacturers are interested in this. So it turns out that they all have different visions or expectations of the traffic control aspect of this. So I'm a little bit curious as to what you see as the evolution of this from the FAA perspective, because I'm sure they want to influence policy in one way, but also at the same time, this is a nascent enough field that there is nothing. The template is a mix of what happens on the ground and what happens in the air. The semi-autonomous thing, in a sense, like it's not fully controlled like the airspace is, neither is it fully free like the ground vehicles are. So how do you see that evolving given how the companies are dealing with it in practice? I mean, slightly separate from the academic viewpoint, but how do you see that evolving?
Yeah, thanks, Lavinia. So that's a really good question. And as I said, when I said research, I sort of did say it's not purely academic, right? A lot of this has to be industry research, and because companies are part of this. Traffic management is key because right now, all that has been established is that it's not going to be the traditional air navigation service provider. And the way it's moving is everybody has their own solution. And there is very little conversation about how these solutions are going to actually interact and play with each other, or even what the guiding principle should be, right? So I think it's the way the initial path forward in all of these things, much like, with aircraft, is you figure out how to operate one aircraft, right? You then figure out how to operate all the aircraft when you get to decide on all of them. And so we're sort of there where it's a combination of either there are only 5 cars on the road, or all the cars belong to the same operator. And I think we're there. Where we honestly do not have any answers is what happens when you actually have different what do the unifying principles, right? How do you ensure that if each of these operators has their own system that's doing the traffic management, how they talk to each other? And that on the research side is where a lot of our more recent work is going in identifying those things, because I think it's similar to the car thing, and that's where we went with the the protocol-based work, sort of inspired by ground transportation, because the idea there is you basically come up with rules that anybody will be able to operate under, right?
Yes.
You can't do more coordinated, more sophisticated coordination if you don't have information sharing. So
yes,
without that, you're going to go to the point where I'm going to look and see, okay, I have 4 cars here, I'm going to let the car on the right go.
Correct.
Right.
Yes. Yes, exactly. Right. Yeah.
I think, that's a good question. And I mean, that's one of the challenges with the autonomy piece. I think maybe the one part which is a little bit less, has been dealt with differently between road and air is on the ground. The mixed autonomy case is very real, right? You're going to have them pretty much in the same space. Whereas right now, at least, with the small drones, you have some segregation, but once you talk about urban air mobility and you have passengers on board, you're not at 200 feet, 300 feet.
Yes. Yes.
And so
exactly.
you have to deal with that mixed autonomy case.
Yes, and it's highly heterogeneous, both in terms of the type and size of vehicles, but also their capabilities in terms of how autonomous or how their sensing capabilities are, and how what their decision-making capabilities are too. So that's interesting. And I think the human plus fully autonomous thing, of course, will be another fairly challenging aspect. So, but this is super exciting. Do you know are there test beds in some sense for some of these aspects? I know some are happening for just like medical drones or some specific applications, maybe even for like package drones as well. But are there either, physical test beds? I guess simulation is the only way people are looking at it right now.
There are similar simulation test beds. There are physical test beds that are slowly coming up, but they tend to be very much at a 4 or 5 vehicles. It's, as I said, most of the work right now is focused on the vehicle, getting vehicles to fly safely and autonomously. They're at that level, and the vehicle mission level. Most of the other work is the testbed work is simulation, numerical simulation based, with some guided physical testbeds as well. A lot of it is in sort of private industry. There are sort of commercial testbeds. There's some of the national labs. I think Lincoln Lab is building one, but I mean, it's very much at very early stages, right? So we've gotten to a point where we realize this is coming and we need to come up with things quickly. So yeah.
Yes. Yeah, it's really exciting for that very reason, I think. Let me see if there are any questions from the audience here. I don't see any questions right now. I was also wondering a little bit about, have you at all thought about the intermodal aspect of this? Like when we think about how people will use it, there is now so many different modes, and I see it competing even a little bit with traditional aviation when you think about especially the spoke to hub kind of flights and so on. How do you see that evolving, or are airlines thinking about this in some way? Now I'm trying to move from the ground, clearly the road car manufacturers, all the way to the airlines. I think we just have a minute, but yeah.
So I think they do. I mean, the airlines are moving, right? I forget, was it? There was an airline that announced bus service between Philly and New York. So the airlines are certainly moving to the ground. I think when it comes to cargo, there are things that we're thinking about when it comes to intermodal aspects, because if you think about last mile, it's not fully clear. It's not obvious that last mile should be drone and not ground. Right. So, or maybe it's the other way around. And similarly, yes, in congested markets, I think one of the urban air mobility cases that people are thinking of is airport transfers.
Yeah.
And so, yeah, you can imagine, I think it's going to be a key thing. Ultimately, as a passenger or as a end customer, when I buy something, I just, I'm agnostic to how the package gets here, as long as it gets here, in good condition at reasonable cost. Right?
Yeah. Okay, well, I think we'll wrap up. Thank you so much for this very exciting seminar. And we'll be posting this seminar online on the TSL webpage, the webinar page, and we'll be sending out an announcement to the TSL community about that. Thank you everyone for attending, and thank you, Hamza, especially for speaking about this. I really appreciate it.
Thanks for the opportunity. Bye. Have a good weekend.